Right now on the eastern coast of Sicily, Europe's most active volcano is doing something it has done thousands of times before, and yet this particular stretch of activity has managed to catch even the scientists who study it most closely off guard. Over the past several days, Mount Etna has been producing intense explosive bursts from its Voragine crater, hurling volcanic bombs into the summit area while a thick plume of ash drifts south and southwest across the island. Catania Airport, one of the busiest in southern Italy, has repeatedly suspended arriving flights as ash drifted into flight paths. The Toulouse Volcanic Ash Advisory Center has kept the aviation warning locked at red, the highest level on the scale. At the same time, glowing rivers of lava have been pushing down through the Valle del Bove, one of the volcano's most dramatic natural amphitheaters, while a separate fissure higher up near the Valle del Leone continues to feed its own flow. Multiple vents, multiple eruption styles, all happening at once, on a mountain that has already produced more than 240 distinct explosive episodes since 1986, alone. But here's the part that's genuinely surprising, and it isn't really about this week's ash cloud or this week's lava front. It's about a discovery published earlier this year that has forced volcanologists to rethink something far more fundamental. Not just what Etna is doing right now, but what Etna actually is, where its magma truly comes from, and why, after more than a century of serious scientific study, this one mountain has managed to break every rule the textbooks use to explain how volcanoes form in the first place. If volcanoes, deep earth science, or stories about scientists rewriting long-held assumptions genuinely interest you, drop a comment and let me know what you'd like to see covered next, because it directly shapes what gets researched and made into the next video. And if you want to catch the next update on this story, because Etna's activity is still evolving as we speak and the research behind it is still developing too, go ahead and subscribe now so you don't miss it. Let's get into what's actually going on beneath Sicily. To understand why this recent discovery is such a big deal, you first need to understand just how unusual Mount Etna already was, even before anyone found anything strange about its magma supply. Etna rises more than 3,000 meters, close to 10,000 feet above the eastern coast of Sicily, making it the tallest active volcano in Europe by a wide margin, and its documented eruptive history stretches back to roughly 1500 BCE, giving it one of the longest continuously recorded histories of any volcano on the planet. It isn't just historically active, it's actively active, in the most literal sense of that phrase. Eruptions occur multiple times a year, sometimes several times in a single month, ranging from relatively mundane summit degassing and small ash puffs all the way up to dramatic paroxysmal events, sudden intense episodes of lava fountaining that can send incandescent material hundreds of meters into the night sky and produce ash columns tall enough to disrupt regional air travel across the entire central Mediterranean. This particular summer has offered a compact tour of nearly the full range of what Etna is capable of. Back in late June, a new effusive eruption began when a fracture opened near the base of the northeast crater at an elevation of roughly 3,000 meters, sending a slow-moving but relentless lava flow down toward the Valle del Leone. By early July, monitoring stations were picking up fresh lava fountain episodes at the Voragine crater, feeding flows that spilled over into the neighboring northeast crater, while a second fissure vent opened in the Valle del Leone at close to 2,700 meters elevation, sending its own flow past a landmark called Monte Simone and down into the Valle del Bove. Then, on the morning of July 30th, Etna produced a genuine paroxysm at Voragine, a particularly intense phase of sustained lava fountaining, preceded by hours of weak Strombolian activity that abruptly ramped up around 3:30 in the morning local time, accompanied by volcanic tremor climbing to a sustained high plateau. And the activity has kept building since, with intense, continuous explosive output at Voragine through the first half of August, volcanic bombs falling in the summit area, ash spreading toward the south-southwest, and two separate active vents feeding complex overlapping lava fields down toward the northern wall of the Valle del Bove. None of this, on its own, is actually unprecedented for Etna. This is, in a very real sense, simply what the volcano does, and has done, for tens of thousands of years. What makes this year different is not the eruptions themselves, but a piece of research published just a few months before this latest sequence began, research that finally started answering a question that has quietly frustrated volcanologists for decades. Why does Etna exist at all, in the specific form that it does? That might sound like a strange question to ask about a volcano that erupts constantly and has been studied by some of the most sophisticated monitoring networks on Earth. But the honest answer, until very recently, was that nobody fully knew. Here's why that question is so much harder than it sounds. Volcanologists have historically organized nearly every volcano on the planet into one of three broad families, based on the tectonic setting that generates the magma feeding it. The first family forms at divergent plate boundaries, places where two tectonic plates are slowly pulling apart from each other, most commonly along the mid-ocean ridges that snake across the floors of the world's oceans. As the plates separate, hot mantle material rises to fill the gap, and the drop in pressure as it rises allows that material to partially melt, generating a steady, relatively predictable supply of fresh basaltic magma. The second family forms at subduction zones, where one tectonic plate is forced downward beneath another, exactly the setting behind the Pacific Ring of Fire, and behind the Cascadia subduction zone that has been generating its own headlines further afield this year. As the descending plate sinks into the hotter mantle below, water trapped within its minerals gets released, and that water lowers the melting point of the surrounding rock, enough to generate fresh magma, which then rises to feed volcanoes along the overriding plate's edge. The third family forms over hotspots, fixed plumes of unusually hot material rising from deep within the mantle, independent of any plate boundary at all, the mechanism most commonly associated with the volcanoes of Hawaii, where a stationary plume has punched a long chain of islands into the crust as the Pacific plate slowly drifts overhead. Every other major volcano you can think of fits reasonably well into one of those three categories. Mount Etna does not, and this mismatch has bothered geologists for a very long time. Etna sits close to a genuine subduction zone, the boundary where the African plate is being forced beneath the Eurasian plate along the edges of the Mediterranean, so on paper it should behave like a fairly standard subduction volcano, chemically similar to the other volcanoes scattered along that same tectonic boundary, places like Vesuvius or the Volcanic Islands further out in the Tyrrhenian Sea, but it doesn't. The chemistry of Etna's lava consistently resembles something closer to what you'd expect from a hotspot volcano, alkaline-rich magma with a geochemical signature that doesn't cleanly match the subduction-driven volcanoes sitting nearby. And it can't be a straightforward hotspot either, because there's no evidence of the kind of deep, stationary mantle plume that would be required to sustain that kind of activity in this exact location, and no chain of progressively older extinct volcanoes trailing off in a consistent direction, the way you'd expect if a plate had been slowly drifting over a fixed plume for millions of years. Etna, in other words, has spent decades sitting in a kind of scientific no-man's land, clearly volcanic, clearly connected to the tectonic activity happening around it, and yet stubbornly refusing to fit cleanly into any of the three explanatory boxes available. That is exactly the puzzle. A team of researchers led by Sébastien Pilet at the University of Lausanne, working in collaboration with Rosa Corsaro at Italy's National Institute of Geophysics and Volcanology in Catania, set out to resolve, and the answer they landed on, published this year in the Journal of Geophysical Research. Solid Earth is genuinely one of the more elegant pieces of detective work to come out of volcanology in recent memory. Rather than looking only at Etna's current eruptions, the team dug into the volcano's much longer geological memory, analyzing 85 separate rock samples collected from lava layers across eastern Sicily, representing roughly 500,000 years of the volcano's history, and stretching back to include much older, smaller eruptions from a separate volcanic region south of Etna called the Hebelian Plateau. What they were looking for was consistency, or the lack of it, in the chemical fingerprint of the erupted material over that enormous span of time. What they found was remarkable, specifically because of how little it changed. Despite Etna growing from what was likely a modest volcanic center into the roughly 10,000-foot giant that towers over Sicily today, despite producing something in the neighborhood of 83 cubic miles, or around 346 cubic kilometers, of alkaline lava over a period of roughly 60,000 years alone, the underlying chemistry of the magma stayed remarkably steady throughout. That kind of consistency doesn't fit comfortably with the idea of magma being freshly generated over and over again through ordinary melting processes, the way it typically happens beneath a standard subduction zone volcano, because fresh melting events driven by changing tectonic conditions tend to leave behind a chemical record that shifts and varies over time as conditions change. Instead, the steadiness of Etna's magma chemistry across 500,000 years pointed towards something quite different, a magma source that had essentially been sitting in place for a very long time, largely unchanged, simply waiting for a pathway to the surface to open up. That's where the second half of the discovery comes in, and it involves a layer of the Earth that most people have never heard of, called the low velocity zone. This is a relatively weak, partially melted layer, sitting at the very top of the mantle, roughly 50 miles, or about 80 kilometers, beneath the surface in the region under Sicily. It gets its name from the way seismic waves slow down slightly as they pass through it, a telltale sign that the rock there isn't fully solid, but instead contains small pockets of partial melt scattered through an otherwise solid matrix. Similar melt-rich layers have been detected beneath a number of other subducting plates around the world in prior geophysical surveys, so the existence of such a layer beneath Sicily isn't itself the surprising part. The surprising part is what the research team proposes happens next. Rather than that low velocity zone generating brand new magma through the usual process tied to a descending plate releasing water, The team argues that small pockets of magma have simply existed within that layer for an extremely long time, effectively stored there, chemically stable, going essentially nowhere, until the specific tectonic conditions found beneath Sicily gave them a way out. And what provides that way out isn't a rising plume of hot material, the way a hotspot works, and it isn't a straightforward release of water from a subducting slab, the way a typical subduction volcano works. It's mechanical stress. As the African plate collides with and bends beneath the Eurasian plate in this specific corner of the Mediterranean, that bending motion cracks and fractures the base of the crust immediately above the low velocity zone. In a process the researchers compare to squeezing liquid out of a sponge, those fractures create a pathway, and the pre-existing pockets of magma sitting within the low velocity zone get physically squeezed upward through them, migrating toward the surface, not because they were newly created, but because plate motion finally gave them somewhere to go. The research team has tied this specific mechanism to something called petit spot volcanism, a category of volcanic activity first identified by Japanese geologists back in 2006, describing tiny submarine volcanoes found scattered above bending oceanic plates near deep-sea trenches in the Pacific. Those petit spot volcanoes are small, typically only a few hundred feet tall, barely noticeable bumps on the ocean floor compared to a true giant like Etna. But the underlying mechanism, pre-existing melt squeezed upward by plate bending rather than freshly generated by melting, appears to be essentially identical. If the Lausanne team's interpretation holds up, Mount Etna would represent something that has never been documented before anywhere on Earth. A full-scale, continental, stratovolcano-sized eruption of the same petit spot process that has, until now, only ever been observed in miniature, on the floor of the ocean, far from land, far from any town, and far from any observation network. That reframing matters, and it's worth sitting with why for a moment, because it effectively creates a rare fourth category sitting alongside the three classical explanations for how volcanoes form. Petrologist Sarah Lambart at the University of Utah, commenting on the findings after they were published, described the implications in fairly direct terms, calling it a new type of volcanism precisely because it highlights an interaction between the crust and the upper mantle that had been largely overlooked in how scientists think about where large volcanoes come from. It isn't that the three traditional categories were wrong, it's that they were incomplete, built primarily around observations of typical-sized volcanic systems, without fully accounting for the possibility that an unusually large volcano could be fed by a fundamentally different mechanism, hiding underneath a setting that looks, on the surface, like an ordinary subduction zone. There's also a deeper story buried in how this discovery reshapes Etna's earlier history, one that connects the volcano's massive modern form all the way back to a much smaller, older, and mostly forgotten set of eruptions. South of Etna sits the Hyblaean Plateau, a region of southeastern Sicily where much older, much smaller eruptions took place long before the modern Etna edifice began building itself up. On their own, those Hyblaean eruptions have always looked like a fairly minor, disconnected footnote in Sicilian geology. But when the research team examined the chemistry of that older material, they found a connection to the same deep, low-degree melt source now proposed to feed Etna itself, suggesting that some of that ancient magma had, at various points, stalled on its way toward the surface, cooled in place, and chemically altered the surrounding mantle rock before later batches of related magma remobilized and pushed through in subsequent episodes. Rather than treating Etna and the older Hyblaean volcanism as two separate, unrelated stories, the new interpretation links them into a single, much longer continuous narrative. One process, quietly operating beneath this corner of Sicily for an extraordinarily long stretch of geological time, occasionally breaking through in small, scattered eruptions in the deep past, before eventually scaling up into the enormous, near-constant volcanic system towering over Catania today. It's worth being honest about the limits of this new interpretation, too, because the researchers themselves are careful to frame it as a compelling hypothesis built from indirect evidence rather than a fact confirmed by direct observation. Nobody has drilled 50 miles down into the earth to physically sample the low velocity zone beneath Sicily, and nobody realistically could with any technology that exists today. The case rests instead on a combination of long-term rock chemistry, tectonic history, and geophysical clues about how seismic waves behave as they pass through that deep layer. A strong, carefully constructed circumstantial case rather than a smoking gun. But even acknowledging that uncertainty, the model succeeds at something that decades of prior attempts to classify Etna had failed to do. It offers a single coherent explanation for why Etna looks geochemically strange compared to its subduction zone neighbors, why its magma supply has remained so chemically consistent across 500,000 years despite the volcano's dramatic growth in size, and why a location that shouldn't, according to the standard three-category model, be capable of sustaining a volcano of Etna's scale, somehow is. This isn't the only piece of genuinely new science to come out of Etna in the past year either. And the second discovery adds an important layer specifically relevant to understanding the kind of eruptions happening on the mountain right now, this week, as flights get suspended and lava pushes down through the Valle del Bove. A separate study published this year and focused on one of Etna's most violent historical eruptions, an event dated to around 122 BCE that produced a mafic Plinian eruption, an unusually powerful, high-column, explosive event for a volcano whose eruptions are more typically associated with fountaining and flowing lava, rather than the towering, sky-darkening columns usually associated with far more silica-rich volcanoes, examined exactly what made that particular eruption so much more explosive than Etna's usual behavior. The research pointed to the specific roles of two dissolved gases carried within the rising magma, carbon dioxide and water, and found evidence that these two components can drive genuinely separate explosive pathways depending on how deep in the system they're released from solution. Magma, rising from deeper origins, tends to be dominated by carbon dioxide degassing earlier in its ascent, while water tends to come out of solution much closer to the surface, and the specific combination and timing of those two processes appears capable of tipping an otherwise fairly typical Etna eruption into something far more violent and far more explosive than the mountain's usual pattern of activity. That distinction matters directly for understanding the mixture of eruption styles Etna has been producing this particular summer. Simultaneous effusive lava flows quietly working their way down through the Valle del Bove, alongside sudden, violent paroxysmal fountaining at Voragine, capable of sending ash high enough to ground commercial flights. Rather than being two disconnected phenomena, both may trace back to the same underlying magma plumbing system expressing itself differently depending on exactly how deep gas release happens to occur on any given day. Taken together, these two pieces of research, the deep, ancient, low-velocity zone reservoir feeding the volcano over hundreds of thousands of years, and the shallower gas dynamics determining whether any individual eruption leans effusive or explosive, offer something volcanologists have wanted for a very long time, a genuinely mechanistic understanding of why Etna behaves the way it does, rather than simply a very long, very detailed historical record of what it has done. And that distinction carries real, practical weight for the people who live in its shadow. More than 750,000 people live directly within the area Etna could plausibly affect during a significant eruption, including large portions of the city of Catania itself, and the volcano's constant low-level activity means monitoring. It isn't a matter of watching for rare, dramatic warning signs, the way scientists might watch a long-dormant system elsewhere in the world. It's a matter of continuously interpreting an enormous, never-ending stream of data, a seismic tremor, ground deformation, gas emissions, thermal imaging, trying to distinguish the routine background hum of a volcano that erupts constantly from the specific signals that precede a genuinely dangerous escalation. If tectonic stress really is the primary switch controlling when and how much of that deep, pre-existing magma gets squeezed upward, as the low-velocity zone research suggests, then that reframes exactly what monitoring networks should be paying the closest attention to. Rather than focusing primarily on signs of fresh magma generation deep beneath the volcano, the way scientists might approach a more conventional subduction zone system, the new model suggests that tracking the fine details of regional fault movement and crustal stress accumulation around Etna could become an increasingly important piece of the forecasting puzzle, since it's that mechanical squeezing, not fresh melting, that the research now identifies as the actual trigger controlling how much stored magma escapes and when. That's not a tool that lets anyone predict the exact date of the next paroxysm. This kind of research doesn't produce that sort of precision, and nobody studying Etna claims that it does. But it does offer a clearer, more physically grounded picture of what's actually happening beneath the surface, which is precisely the kind of foundational understanding that eventually translates into better early warning capability, refined hazard maps, and more informed decisions about exactly where it's genuinely safe to keep building and living around a mountain that has no intention of ever fully going quiet. There's a broader scientific significance here too, one that extends well beyond Sicily itself. Because if Etna really has been operating according to this Petit spot mechanism all along, that raises an obvious and genuinely open question. If pre-existing pockets of ancient melt sitting in the low velocity zone can be squeezed upward at large enough scale to build the tallest, most active volcano in Europe, are there other large volcanoes around the world that might be feeding off a broadly similar hidden mechanism, misclassified for decades simply because nobody had gone looking for this particular signature before now? The research team has been fairly direct in suggesting that Sicily could serve as something of a natural laboratory for testing exactly that question elsewhere, examining whether other volcanoes sitting in geochemically ambiguous settings, places that never quite fit cleanly into the three traditional categories either, might likewise trace back to deep, long-stored mantle melt being liberated by plate bending and crustal fracturing rather than fresh magma generation. That's precisely the kind of finding that tends to ripple outward through an entire field once it's published, prompting other research groups working on other seemingly mysterious volcanic systems around the world to revisit old data with an entirely new hypothesis in mind, one that simply didn't exist as an option before this year. So where does that leave things right now, with ash still drifting over Catania and lava still advancing through the Valle del Bove as this gets recorded? The activity unfolding on Etna this particular week is not evidence that anything has fundamentally changed about the volcano, and it isn't a signal that the new research somehow makes the mountain more dangerous than it was before scientists understood where its magma actually comes from. Etna has behaved this way, cycling through effusive flows and explosive paroxysms for hundreds of thousands of years, long before anyone had any theory at all about the low-velocity zone sitting 50 miles beneath it. What's genuinely different is the depth of understanding now available to the scientists watching it happen. For the first time, there's a coherent, evidence-based explanation connecting Etna's unusual chemistry, its remarkable long-term consistency, its unmatched frequency of eruption, and its position in a tectonic setting that never quite made sense under the old three-category framework, into a single unified picture. That's not a small thing in a field where major volcanoes have sometimes been observed and monitored for over a century without anyone fully agreeing on the basic mechanism driving them. It's also worth stepping back and appreciating just how unusual it is, in a broader sense, for one of the best studied, most continuously monitored volcanoes on the entire planet to still be capable of producing a genuinely paradigm-shifting discovery this deep into the modern scientific era. Etna sits within reach of some of the most sophisticated volcanological infrastructure in the world: dense seismic networks, continuous gas monitoring stations, satellite-based ground deformation tracking, decades upon decades of meticulously logged eruption records reaching back centuries. And despite all of that instrumentation, despite generations of dedicated researchers walking its slopes and sampling its lava, the actual source of its magma, the fundamental question of where all of this material has been coming from for 500,000 years, remained genuinely unresolved until earlier this year. That's a useful reminder that even the most intensively studied places on Earth can still be hiding something fundamental about how they actually work, simply waiting for the right combination of long-term data, careful chemical analysis, and a willingness to question three categories that had been treated as complete and sufficient for the better part of a century. For anyone living on or visiting the slopes of Etna, or simply following the current eruption sequence from afar, the practical picture remains largely what it's always been. Italian authorities and the observatory in Catania maintain continuous, sophisticated monitoring of the volcano, precisely because of how frequently it erupts. And the aviation color code system, currently sitting at red because of the ongoing ash emissions, exists specifically to manage the most immediate and far-reaching hazard this kind of activity produces: disruption to regional air travel from ash reaching cruising altitude. Lava flows, while visually spectacular and capable of destroying anything directly in their path, tend to move slowly enough on Etna's slopes that they rarely pose a direct threat to human life, which is part of why the volcano, despite erupting almost constantly, has such a comparatively low historical death toll relative to how active it actually is. The genuine ongoing hazard management challenge is less about any single dramatic eruption and more about the accumulated decades-long process of understanding a system that never fully rests, and this year's research represents a meaningful step forward in exactly that long, patient process. So here's a genuinely interesting question worth sitting with, and I'd love to hear what you think about it in the comments. If one of the most heavily monitored volcanoes on the entire planet could keep a secret about its own fundamental origin for over a century of dedicated scientific study, what does that tell us about how much we still don't fully understand about the other volcanic systems we've spent far less time and far fewer resources studying carefully? That's not a rhetorical scare tactic. It's a genuinely open question that researchers are only now starting to seriously ask, and it's exactly why stories like this one are worth following closely rather than treating as a one-time curiosity. If this helped you understand the real science behind a headline about lava and ash that's easy to scroll past without ever grasping what's actually happening deep underground, share it with someone who'd find the mechanism behind it as fascinating as you clearly do. And subscribe if you want to stay with the story as it keeps developing, because Etna is still actively erupting as this gets published. The research into exactly how far this petit spot mechanism might extend to other volcanoes worldwide is still ongoing, and there's a genuinely good chance we'll be revisiting this exact mountain again soon with even more answers. We'll keep tracking it closely as the data comes in.